So now we discuss transformer. We'll move towards transformer gradually, right? So quick recap of attention again. We have an encoder layer, a decoder layer, right? The queries are coming from decoder, keys are coming from encoder, right? Then we have the dot product, right? And then we basically get the softmax, and from softmax we get the what weighted sum, and from weighted sum we get the attention output, right? So attention values, attention distribution, attention output. Okay. Now think about it. So he asked the question that if the attention mechanism allows you to access all the tokens, right? By the way, remember, attention, I mean, if you already have, forget about machine translation, if you already have two sequences given, you can actually use attention in parallel, isn't it? Not in case of machine translation. Let's say you have two sequences, and your task is to align two sequences. That's all, right? You are given two sequences, and your task is to align two sequences. It's not an expert prediction task. Then you can compute attention in parallel, because you are already given all the tokens. And attention values are not dependent on the tokens on each other, right? So the question that he asked is that if through attention you can access to all the input tokens, why do I need this connection, right? So why? So this is my encoder, right? And this is my decoder, and I already said that each decoder state can have access to all the encoder states, right? Even in parallel, if it's an alignment problem. Why do I need this? Because these are the culprits. Why? Because of this recurrent dependency, you are not able to process tokens in parallel. If these connections had not been there, you could have accessed all the tokens in parallel, right? Isn't it? If these connections had not been there, you could have accessed all the tokens in parallel. And in self-attention, we will do this. Okay. So in self-attention, what we do, we will remove the temporal dependency. We will remove this recurrent connection, right? And we allow the decoder states to access to all the encoder states. Can you think of a problem here? If we do that, if we remove all this sequence connections, what's going to the problem? What's going to the problem? So basically you have this, right? You have this. These are encoder states, these are decoder states, right? Each decoder state can access to encoder states separately, in parallel, right? What's the problem? Order, right? So x1, x2, x3 and x3, x2, x2 are the same, because you are accessing tokens independent of their positions, right? We will discuss later that if there is a mechanism to incorporate the position information into the model some ways, right? Then you can do this parallel processing, right? So for the time being, you assume that there is a mechanism which takes care of this position information. Okay. Now let's discuss this self-attention, the idea behind self-attention. So in self-attention, what we do, and we will discuss this irrespective of any sequence to sequence model. Just assume that you have an RNN, right? And you want to incorporate this self-attention on top of an RNN. Okay. So this is my input. These are the inputs. right? Or H1, H2, H3 are the hidden states, right? So what I do here is that for every hidden state, from every hidden state, I will generate 3 vectors: query, key, and value. From every hidden state, I will generate Q1, query, K1, key, and value V1. So from H1, I will generate Q1, K1, V1. How I'll tell you later. From H2, I'll generate Q2, K2, V2. From H3, I'll generate Q3, K3, V3. Okay? And how do we do that? Basically, we will use 3 matrices: WQ corresponding to query, WK corresponding to key, and WV corresponding to value. So these are matrices. So basically Q1 is WQ times H1. Okay, K1 is WK times H1. V1 is WV times H1. So from H1, I am generating 3 different vectors through three different linear projections. That's all. And if you want, you can also do some nonlinearity. Similarly, using the same set of matrices, right, I will generate Q2, K2, V2, right, and Q3, K3, V3. Remember, these matrices are being shared across tokens. So for all different inputs, I have the same set of matrices. So parameters are shared. Okay, so I get query, key, value. Then what's the next task? I need to take the dot product between query and key, right? So every query will attend to all the keys. So basically, Q3 will attend to K3, meaning Q3 and K3. We have a dot product between Q3 and K3. Q3 will attend to K2. Q3 will attend to K1. So here I'll get Q3 dot product K3, Q3 K3, Q3 K2, and Q3 K1. Right? Here I'll get Q2 K1, Q2 K2, and Q2 K3. Now here I am assuming that it's an RNN of fixed size and every state can access to all the other states. It's not like only the future, I mean only the later state can access to the previous. All state can access to all the other states. We're assuming that. Similarly, here we'll get Q1 K1, Q1 K2, Q1 K3. Okay, so and what are they? These are attention values, scores. So from attention scores, what's the next task? I'll pass it through sigma. I'll get the distribution. Get some distribution. 3 different distributions, right? Agreed? And then these distributions will provide me the weights, right? Let's say I'll get W1, W11, W12, W13 here, right? What's next? Weighted sum, and this will be W11 times V1 plus W12 times V2. V2 is coming from here, plus W13 times V3. Similarly here. So I'll get an attention vector A1 here, attention vector A2 here, attention vector A3 here. Clear? So we got this query, key, and value, right, from each of the hidden states, right? And then every query basically has attended to all the keys, right? And then we got this vector, we feed it to a softmax, we got a distribution, and the distribution essentially gives you an idea of the weight. And then what we did the weighted sum of the value vectors, right? So, so the major difference between attention and self-attention is that in attention, I mean, in vanilla setup, you need a query and a key. Keys and values are the same, right? And in the sequence-to-sequence model with attention, we showed that the recurrent dependencies are the issues, right? Therefore, we thought that let us just remove the recurrent dependencies and let each of the hidden states, attends to all the other hidden states. Okay, so and you might be wondering why these vectors are called queries, keys, and values, right? So as the name suggests, these names have some resemblance with a typical information retrieval kind of setup where we write a query, right? So when we write a query, what are the keys? The keys are essentially the meta information, the metadata of documents present on internet, right? For example, it can be a set of keywords, it can be the snippet of a document, right? And so on and so forth. So you can think, I mean, this is just an analogy, by the way, okay? So the snippet of a document, the keywords of a document, these are like, I mean, you can consider them as keys, right? And then what we do, given a query, we look at the similarity between the query and the keys of documents, right? And see, here also we are doing the same thing. We are measuring the similarity between query and key using dot product, right? And once the similarity is measured, right, what we do next in the information retrieval setup, we identify the set of documents which are important, right? And we retrieve the document which is, I mean, we basically rank all the documents based on some similarity. And sometimes in information retrieval, I'm not talking about search. Search is different, retrieval is different, right? In search, you just rank all the documents and that's it, right? In retrieval, your task is also to identify the portion of the document which is relevant to the query, right? Let's say you have a book, and while matching the query with the with the key, you identified that book to be relevant, right? But the entire book may not be relevant. Only a part of the book may be relevant, right? Now, how do we get which part of the book is relevant? So this value vector essentially tells you, look, the value vector is obtained from the hidden state with some linear transformation, right? So you can think of this linear transformation as basically retrieving a part of the document apart from the document, right? So your entire document is H, and a part of the document is W transpose H or W times H, right? So you essentially you essentially retrieve only that part of the document, not the entire document. So this is just an analogy, and therefore it makes sense in this context. So self-attention again, pictorially. So for every hidden state, we have query, keys, and values, and we use these three equations to obtain query, keys, and values, right? And then we do dot product, right? And then we pass the dot product through a softmax. It will give you a distribution, and then we do the weighted. We take the weighted sum of the values. Okay. So, and then you basically consider the entire operations that we talked about so far as a layer, right? So layer one, what are the inputs? Your inputs are the tokens and the corresponding representations, right? And I told earlier in last part that that when we remove the recurrent dependencies, right, the position information is gone. So we need some sort of positional encoding here. We'll talk about positional encoding later. So the input to the layer one is the embedding right, embedding, let's say embedding, let's say for this input x1, embedding e1 plus the position information, the positional encoding of e1, x1, right? And you feed this vector to the layer, right? And in the layer, what will happen is that you basically do the self attention operation, and that will give you the attention vectors, right? So attention vectors here will be a1, a2, and a3. That's what we discussed so far. So layer one, so this is layer one. Similarly, you can think of stack of layers where the outputs of layer 1 will be fed to layer 2, and in layer 2 the same set of operations will happen, right? But remember, in layer 2 you have a different sets of parameters. What are the parameter matrices? WQ, WK, and WV, right? So in layer 2 you will have another set of parameters. Layer 3, another set of parameters. So you keep on adding more parameters, right? So there is no dearth of parameters. So you keep on adding more parameters, and that would basically help you understand the document in a better way, with more more informative way, and so on and so forth. So, right, you stack up layers one by one, and you keep repeating the same process. Now here, so far, we assumed that every key, every query is attending to all the keys, irrespective of the position, right? So Q1 is also attending to Q3. Sorry, Q1 is attending to K3, right? Q1 is also attending to K2, right? It is not the case that Q1 won't be able to attend K3. Okay. Later on, we will see a different setup altogether. Okay, so attention, self attention is done. The problem with self attention is that sometimes if we use only one head, meaning only one set of parameter matrices in a layer, you may miss out some information. For example, in case of CNN, right? So what we do in case of CNN is that we apply multiple filters, right? And every filter may correspond to a certain aspect of the image. For example, let's say you are trying to differentiate between cat and dog, and let's say one filter is responsible for identifying the ears, right? One filter is responsible for identifying the tail, and so on and so forth, right? But here, so people thought that, okay, let us essentially use the similar concept here, right, and add more parameters. So from single head self attention, now we are moving to multi-head self attention. And what is multi-head self attention? So same thing, right? So for single head, for every layer, let's say layer one, you have WQ, WK, WV, right? And let's say WQ1, WK1, WV1, the subscript 1 corresponds to layer, right? So using WQ1, WK1, WV1, you will get A1, A2, A3. These are the attention vectors. Now what you do, you add another set of parameters, right? So let's say this is called WQ1111, right? Superscript indicates head and subscript indicates layer. WQ12, WK12, WV12. Okay, so you basically added another set of parameters. You do the same operation. What you will get? You will get another. Right. Let us use this one. Right. 1, 1, whatever. 1, 1. Right. 1, 2, 3. You get another set of attention vectors. Okay. So earlier you had 1 1 1 1 2 1 1 3 1. Now you have 1 1 2 1 2 2 1 3 2. Okay, and and this set of parameters is called head. So attention head 1, attention head 2, similarly attention head 3, and so on and so forth. So the more you add you add heads, you basically add more parameters. Okay, so from every head you get an attention vector, right? So what will happen if we do that? What will happen? So let's say the dimension of the hidden state is d, and from every attention vector, so every attention vector is of size d, right? Let's say you have k number of heads. So how many? So what will be the dimension of this concatenated attention vectors? K times d. K times d, right? K times d. But remember, the output of this layer will be fed to the next layer. So the input to the next layer should be of dimension d. But here we have kd. So we need to project it to a d dimension vector. How do we do that? We use a linear layer with size kd times d, right? We'll add a linear layer here, and this is called output matrix, output projection, right? So we'll, for every token we have this output projection, which will project it to a d-dimensional vector, right? So we concatenate all the attention vectors and we project it. So this is called multi-head attention. Okay, so this is a pictorial, depiction of the entire thing. So this is the concatenated attention vector, and then from attention vector we just follow the same process. Okay, attention seems quite complicated. Self attention seems quite complicated, but it is actually a linear operation. Okay, why it's a linear operation? Let's look at it. So this is key, this is query, this is value. Okay, this is attention distribution, right? And then attention vector. So attention vector is what? Is basically sum over, what is t? What is t? T is the number of value vectors, right? So attention vector is weighted sum over all the value vectors, right? L is the layer or position, I guess. Okay, now if you replace V by WVHT, right? Okay, and you see this WV is independent of T. You can move it outside. So WV comes outside, and now you have this, right? Both alpha and H. What is alpha? Alpha is the probability after softmax, and HT is the hidden state. So essentially, what you are doing, you are multiplying the hidden state with the softmax output. Okay. Now, and this is a linear operation. It's a linear operation. Although you can claim that this softmax is a non-linear operation, so alpha is an output of a non-linear operation. But let's assume that alpha is fixed. Then the remaining operation is linear, right? Right? So self attention doesn't add any non-linearity, and that's the problem. Because if you don't add non-linearity, you won't be able to understand the complex structure of the input, right? So to do that, what we will do now, we will add something called position-wise feed-forward network. Position-wise FFN. Okay, what is position-wise FFN? So this part we have already discussed. Okay, self attention and then attention vectors. What we do now, we will add, let's say this is A1, A2, A3, we add a feed forward network here. And how does this look like? This feed forward network first project a d-dimensional attention vector to a 2D vector, up projection, and then it projects it to D. Okay, this is FFN. And why this is called position wise feed forward network? Because at every position you have this feed forward network. It is not that you concatenate all attention vectors A1, concatenation A2, concatenation A3, and then you have a bulky feed forward network. No, right? But one point to remember is that this FFN parameters, how many parameters are there? There are two matrices, D times 2D and 2D times D. These parameter matrices are shared across tokens. This is very, very important. This is shared across tokens. Okay. Now, I hope you understand why feed forward network, how feed forward network adds nonlinearity. Because if you look at the equation here, so your input is X, which is A in our case. This is up projection plus bias, and this is down projection. So you have two transformation, and then after up projection you pass it through a nonlinearity, right? And then you again do this down projection and then pass it through a nonlinearity. All right. So now within a single layer, what are the two operations? Self attention, feed forward network, right? Let's move on. So far what we have said is that I have a stack of layers, right? And in every layer, tokens, every token can attend to all the other tokens, irrespective of the position, right? But when it comes to next word prediction, I mentioned, right, a language model objective, right? The initial token cannot attend the future token because the future token has not been generated so far, right? So what it means that that Q1 will attend to K1, right? Q2 will attend to K1 and Q2 can attend to K2, right? And Q3 can attend to K1, Q3, K2, Q3, K3. But the important point to note is that when we train such a model, right, during training, I already know the entire token, the set of tokens, right? So how do I let the model? So I will basically protect the model or resist the model forcefully not to look at the future tokens, although the tokens are available during the training time. During test time, it will not be available. So basically, I need to mimic the way the model should perform during test time, right? During training time, I let the model essentially mimic the way we perform things in the test time. You see the point, right? So I will not allow a query at the ith position to attend to the keys in I plus 1th position or I plus 2th position. And how do we do that? We do this as follows. So, and all these operations are matrix operations, remember this, right? So we have a query matrix Q where all the queries are stored, right? Q1, Q2, Q3, Q4, and so on, right? We have a key matrix, right, where all the keys are stored, K1, K2, K3, ... right? When we take a dot product between queries and keys, right, it will basically produce query key dot product where entries would look like this: Q1, K1, Q1, K2 dot dot dot, Q1, K, let's say N, right? Dot dot dot, Q in K1 dot dot dot, Q in Kn. Okay? So in case of language modeling objective, right? Q1, K1 is okay, but Q1, K2 is not okay. Q1, Q2, K1 is okay, Q2, K2 is okay, but Q2, K3 is not okay, right? So what I will do, I will essentially look at the diagonal part and the upper diagonal part, and the upper diagonal part should not be should not exist during the training time. Okay. So what I will do here, I will multiply this matrix with another matrix which would look like this. All the lower diagonal elements will be 1 and all upper diagonal elements will be minus infinity. Why minus infinity? I'll tell you. Okay, so if we multiply this with this matrix, it will give you a matrix like this: Q1, K1, minus infinity, minus infinity, minus infinity, then Q1, Q2, K1, Q2, K2, minus infinity, right? And so on and so forth. Why minus infinity? Because I'll pass these through softmax, right? E to the power x by sum over e to the power x, right? And these are my x's. Okay, so 1 by minus infinity will be 0. Right? 1 by minus infinity is 1 by e to the minus e to the infinity, which is infinity. 1 by infinity is 0. Right? So essentially, after softmax, these terms will vanish. So although during the training time you have tokens available, right? But you essentially do not let the model look at those tokens using this operation, and this is called masking. Okay, and the enter operation is called mask attention, self attention, right? And this is called mask self attention, whatever. Masked self attention. Okay, so yeah, this is what I discussed. Now we are almost done. So we discussed self attention feed forward network, mask self attention feed forward network. Only one part is missing, right? So, and we are discussing everything in the context of machine translation. Remember this, okay? Where you have a source sentence, you have a target sentence. So, the source sentence is in one language, and your task is to translate it to another language. During training time, you have access to the parallel corpus, right? So, source sentence, tokens in the source sentence can attend to all the other tokens. So you can use normal self attention followed by feed forward network. In the target sentence, you can use mask self attention. Okay. So what is missing here is that self attention, right? Feed forward network. Self attention feed forward network. Okay, and so on and so forth. And here you have, so it's the input, mask self attention feed forward network, mask self attention feed forward network. What is missing? The missing part is that there is no connection between this pillar and this pillar, this tower and this tower. By the way, this tower is called encoder and this is called decoder. It's same as the encoder decoder mechanism I discussed for LSTM or RNN. There is no interaction so far between encoder and decoder. Right? How do we do that? we add another attention here, right, after mask self attention, called cross attention. Okay, cross attention. So this is cross attention. This is mask self attention. This is cross attention. What is cross attention? In cross attention, this is again self attention mechanism, right? In cross attention, the query will come from here, and keys and values will come from here. Now remember, after decoding, once the decoding part is done, what is the output of what is the output of the after the encoder part is done, what is the output of the encoder? From the last layer, you'll get again some attention vectors, right? Let's say this is A1, A2, A3, A4, right? And after the mask attention, what is my output? What's the output? Again, set of attention vectors, right? Let's say I call it decoder, so D1, D2, D3, and D4, right? Now from D1, D2, D3, D4, I will generate queries, Q, and from A1, A2, A3, A4, I will generate keys and values. So I am basically adding another set of parameter matrices for cross attention. Okay. Remember one point. This cross attention block will be there at every layer. So at every layer you have different set of parameters for cross attention. Okay. But every layer of cross attention will attend to the final layer of encoder. It is not that the first layer of cross attention in decoder is attending to the first layer of attention in encoder. It's not that. So encoder part is done. You get the attention vectors, and then your cross attention will attend to that those set of vectors. Yeah, you can make multi-headed. Yeah, multi-headed. It is multi-headed. Okay. So using this, you let the decoder model interact with the encoder model. So this is the architecture of transformer. So we have covered more or less all the components. So this is my input. This is a positional encoding that we have not discussed so far. Input and the positional encoding will be added. Now this will be fed to the first layer of the encoder. We have multi-head self attention, right? I will discuss this later. Then we have a feed forward network, right? So this is one block, and you repeat these blocks n times. N can be 6, can be 12, can be 24, and so on, right? So this is one encoder block. One decoder block would look like this: masks, multi-heads attention, self attention, cross, multi-head attention, and then a feed forward network. Okay. Now in between, you see there are some components here and there. So one component is this residual connection. You see, after every submodule within the layer, we have a residual connection. And why residual connection? So we know the beauty of ResNet, right? It helps address a vanishing gradient problem, right? And so on and so forth. And you also see that there is this small layer called add and norm, right? This is a normalization layer, right? In normalization layer, what we do, so we all know batch norm, right? But what they said is that batch norm has certain problems because batch norm is dependent on the batch, right? What is the batch? Batch is a set of instances. And remember, here you are dealing with sequences of texts. So text can be of different length. So within a batch, you may see, right, instances of different lengths. So therefore they said that let's use layer normalization. And what is layer normalization? In batch normalization, we basically take the average across all the instances in the batch, and in the layer norm, we essentially take the average across all the features of an instance. So it is independent of the length of an instance. Okay, and they showed that this gives more stability and stuff like that. That's all. Okay, that's all about transformer. The only part which was missing is positional encoding. I will very briefly talk about positional encoding here. Please go back to my previous year's lecture. I made a full I took a full lecture on positional encoding where we discussed different types of positional encoding using the rope embedding, right? Along with the rope embedding, which is the state of the art recently. But I will not discuss here anything about positional encoding, but only this part, only the transformer. In the transformer paper, they came up with a notion of sinusoidal positional encoding, right? This I will discuss very briefly. Okay, so what is the length, and again, what is the purpose of the positional encoding? The purpose is to encode the position. And why do we need that? Because the recurrent connection is not there, right? So in the transformer paper, they came up with this very weird kind of formula, right, which apparently looks quite dangerous, right? And some of these numbers, why 10,000, why not 1,000, why not 100, I don't know, nobody knows, right? But empirically this turned out to be very interesting, and this is also independent. So you do not need to learn the positional embedding, right? Sometimes you want to learn, but in this case you don't need to learn. And it has it also basically captures the periodicity among across positions. So look at here. So what is this? Let us first look at the formula. So it says that what is pos? POS. Pos is the position of the token, right? Position of the token. What is I? I is one element in the position embedding vector, right? Let's say for the first position, this is my positional encoding, okay, which is a vector. For position 1, for pos 1, this is my vector, right, where I indicates the elements. Not exactly the element, but I corresponds to the elements of the vector, right? So if I equals to 0, then this would be, let's say you are interested in generating the position information for the first position, for the first token. So this will be 1, 0, right? What is, forget about 1. So essentially it will give you the entry for the 0th position. This is 0th position. And this will be 1 when I goes to 0. So this will give you the entry for the first position. When I equals to 1, this will be 2 and this will be 3, right? So you get the second element from this and the third element from this, right? So you see that in the vector, the first element comes from sine and the second element comes from cosine. Okay, why sine, cosine? Again, please go back to my previous year's lecture, you'll understand. Okay, I'll just give you an empirical some example. So EW is the embedding of the vector, which is coming from what to wake, for example, and this is my positional encoding. Okay, sine, cosine, sine, cosine, sine, cosine, right? And you see here, so this corresponds to the case when I equals to 0, right? And this is also I equals to 0, but the second position. This is I equals to 1, I equals to 1, right? And then I equals to 2, I equals to 2, and so on and so forth. So this is my position information, positional encoding. I just add them and pass it to the next layer. There are many papers which showed that we don't need all these things, because since we have a lot of data, right, we can also learn the positional encoding, right? You just assume that it's also learnable parameter, the vector, it's also learnable parameter. The way you are learning other vectors, you also learn the position. Okay, but then learning might be difficult. static embedding might be useful. Then people came up with this idea called rotary positional encoding. Right? Please look at this paper. This is a wonderful paper. That's it about transformer. Okay. In the next class, we will discuss different pre-training strategies. Okay. We'll briefly discuss BERT, BERT, and T5 very briefly. Okay. Thank you.